Okay, so good afternoon. So I'm going to start just a final session for the day. So I've got a couple of things that I would like to talk about. So there are sort of two reasonably disjoint problems that I'm going to address in this lecture. So one is kind of simple, and one is a little bit more challenging. So I'm sorry that late in the day I'm going to maybe make a slightly more challenging example, but I'm trusting you to ask me when I become a So the first sort of setting that I'm going to talk about, when we were using HState, which is this measure of dependence between X and Y, we were just given the data and we were testing it. Okay? But one thing we might be interested in is, well, what if we're not just given data to test, but what if we're actually actively trying to maximize dependence, right? And a nice example about this might be something like feature selection. Like maybe I want to care about the features that have the highest dependence with the labels. They're probably pretty smart features for predicting the labels, right? Now you could also imagine something simpler than just label classification. So maybe I have like a bunch of data, and I want to find a clustering of that data such that the data are most dependent on the cluster labels. So I have no labels, it's unsupervised, but once I've arranged the data into clusters, these clusters have labels, and I arrange the data into clusters in such a way as to maximize the dependence of the clustering, the data on the labels that are assigned, the cluster labels. So this is ways of basically using dependence measure to discover structure in data. I might discover structure by finding features, or I might discover structure by clustering in such a way that I maximize the dependence of the cluster labels on the features of my data. Okay. So this is one class of problems I can talk about. The second class of problems that I want to talk about is this very recent work on using these expected features of probabilities to do inference. So if I get expected features of a probability, you might think, well, I've got a representation of a probability, but what do I really want to do with probabilities? I want to basically make models and then do inference on them. I want to say, like, if I'm a robot, given information from my senses, where am I in the room? So this is, when I have representations of probabilities, one of the key tools that I might want to apply is to, determine my belief about one part of my model given observations of another part. So far I've just said, okay, like a probability is expected features, and that's fine, like that tells me how to represent probabilities. But what if I have a probability like over the location of my robot given the sensor readings? I haven't shown you how to do that. So this is something I think is quite exciting because it really opens up the kinds of problems that I can attack using these expected feature representations. So I'm going to hopefully have the chance to talk a bit about these. Okay, but that's a little bit hard. So that's why it's last. Okay. So first of all, feature selection. There's many ways to select features. I'm going to be talking about examples of feature selection methods that we've applied in microarray data. So that's, I think, a domain which has been very, very exhaustively looked at. One of the things that we've discovered is that many of the ways that people have used to discover features in microarrays end up being just optimizing this HSIC criteria. So that's something that we found. But I think more importantly, it's not always clear from this prior work where you're justified in using nonlinear features. So when you're computing this HSIC quantity, you can use either linear or nonlinear kernels. If you're doing nonlinear kernels for microarrays, like when should you do that? And when you're doing it, like what does it tell you? So this is, I'm going to try and make a little bit concrete, how to use HSIC for feature selection, and then when you're justified in using nonlinear kernels and when you shouldn't bother. Okay. So our algorithm, I'm going to use slightly different notation for it, but I'll explain it. Is going to basically start with all of the features and then eliminate features backwards in such a way as to maximize the increasing dependence with the labels. So why might I eliminate features backwards and upwards? So why should I start with all my features and then throw them away in such a way to increase dependence? Like another way I could track it would be to start with no features and then add features in a greedy way to maximize the dependence, right? So in some cases, both methods are equivalent, but in other cases, the backwards one will find features which the forwards one will not. So imagine you have two features whose product predicts the label. Okay? Then if I see any, like either feature individually, maybe it tells me nothing about the label, but when I see both features together, it tells me a lot. Okay? So if I'm doing backwards elimination, I'll start with all my features, and then if I throw out one of the two good features, then suddenly my dependence will drop, and that's no good. So I'll know that I made a mistake. I'll know that like these two features have to come together. But if I'm selecting features forward, and I choose just one of these two features to add, I'll see no increase in dependence. So now that feature is useless. But actually that's a mistake. The feature is useful, but it's only useful together with another of the features. So forward selection is no good if you've got these nonlinear interactions. But if you don't have nonlinear interactions, then forward selection and backwards elimination are the same. Okay. So here is our algorithm. So this is, I think, complicated notation for a very simple idea. Our output is the ordered set of features, like ordered from least to most useful, and then your input is the full set of features. Okay? So let's forget about this third line for the moment, and I'll come back to that. So what we would do is we would start by computing HSIG between the variables with all their features included and the labels, and then I would remove, either one by one or maybe in blocks of 10 or so features from my feature set in such a way as to maximize my increase in HSIG. So if I remove noisy features that have no meaning, my dependence is going to go up. Okay? And then, I just remove those features from my feature set, I append them to my list, always at the end of the list, so that I'm getting from least to most useful, and then I iterate. So what you now might have noticed is that my HSIG is a function of a kernel, and the kernel has a parameter. So if I'm using an exponentiated quadratic kernel, I might have a bandwidth. Okay? So here I'm writing HSIG not in the notation that I was using before, but in the notation of it having a set of features and a bandwidth, because these are the important parameters now. Okay? So what you might discover as you change the dimension of the problem is that the bandwidth, which gives you your most sensitive test of dependence, will change, because if I'm going from 100 dimensions to 10 dimensions, like the correct bandwidth is not going to be the same. So a heuristic that we've used is that once we've removed a chunk of features, we just maximize the bandwidth, like we choose the bandwidth to maximize the HSIG. A smarter thing to do would be to maximize the ratio of this to its standard deviation for the same reason that we had to maximize MMD ratio to its standard deviation when we were looking at maximizing test power. But that's another story. So the main thing is that, if you've got an HSIG with a nonlinear kernel, you do need to adjust the kernel parameter as you iterate, because otherwise you're not going to get a same answer. Okay, so very simple. Backwards elimination of features to maximize dependence labels. Okay. So there is a whole bunch of methods for selecting features in microarrays, and one of the simplest ones is just a mean difference feature, right? So what is mean difference? Mean difference is like I've got a feature and I look for the, my most relevant features are the ones where the mean is the most different from class 1 to class minus 1. Like that's probably a pretty good feature. Okay. So it turns out that for this simple difference in means features, I can write it as an HSIG. Okay. So what I'm going to do is I'm going to use a linear kernel on my inputs. Okay, so k on my inputs is now just the dot product of like k of x and xi and xj is just xi transpose xj. Okay. Now, if that's the case, then my kernel is just a sum of the kernels on the individual dimensions, right? So, if my ijth entry of k is just xi transpose xj, I can write that as the sum over L of the lth entry of xi times the lth entry of xj, xjl, right? And so that means that my total kernel I can now write as the sum over L of the individual kernels between the nth entry of xi and xj. So I'm going to write that as sum over k L, where L just means the product of the nth coordinate of xi and xj. Does that make sense? So this is true when I'm using just the standard dot product between xi and xj. It means my kernel is just the sum of the kernels, where the kernels just contain the products of those individual coordinates. So the nth kernel contains the product of the nth coordinate of xi and the nth coordinate of xj. Okay? So this is my kernel on my inputs, right? So remember, this is my HC, that's the centered k times the centered L, and I take the trace, so the sum of the diagonal entries. So this amounts to sort of taking the sum of the entry-wise product of k and L. All right? And now for my output kernel, for my L kernel and my labels, well, this is pretty easy. I just have 1 on the number of positive labels as my entry for the first class, and 1 on the number of negative labels with a minus sign for the entry of the other class. Okay? So basically, like my L matrix is a rank 1 matrix. Okay? My L matrix is equal to the outer product of, so let's say, the first half of my positive labels, the second half of my negative labels. So here I do 1 on the number of positive labels all the way down, 1 on the number of positive labels, then 1 on the number of negative labels, 1 on number of negative labels. And there's a minus sign here for the second half. And so I do this, and then the same thing transpose. Okay? So if I do this, and if I use this linear kernel, and if I compute this trace of KHLH, well, because of the way that I've constructed the L, the mean of this column is 0, right? So if I pre-multiply by something that centers the matrix, so removes the mean, well, it has no effect. So if I pre-multiply this by H, it has no effect on this column. If I post-multiply this by H, it also has no effect because the mean is 0. Because I've got 1 on the number of positive points minus 1 on the number of negative points, so it cancels. And so then, you know, this trace of KHLH just becomes trace of K times L. And when you multiply everything out, all you get is 1 on the number of positive points times the sum, well, what I get out is basically like the average of the nth coordinate for the positive class minus the average of the nth coordinate for the negative class. Okay? So in other words, just the average difference of the nth coordinate. And that's like the score for the nth matrix here. Okay? And then when I take the sum of those, that's my complete HC. So this is quite nice. So I can then, if I want to maximize my dependence between my inputs, my features, and my labels, I just choose the L features with the largest of these. Okay? So it becomes rather easy. I just choose the L features with the largest difference in feature means. So this is like a rather complicated way of saying a very trivial thing, which is smart features are the ones who have big differences in means across the classes. Okay? So let's say something a little bit less trivial. I use the same kernel on my K's, but now for my L's, I use this rather complicated two-dimensional matrix of features. Okay? So this matrix has, you know, a vector of 1s of the size number of positive samples divided by number of positive samples minus etc., etc. So it's a little bit messy. But the upshot is that if I use this slightly more complicated label matrix, and then I define my L as being this times its transpose, so the outer product of this and its transpose, then I get the following criterion for my features, okay? So here I'm saying that a smart feature is one where the difference between the positive features and the global mean, the mean across positive and negative, plus the difference between the negative features and the global mean is large. So I'm saying that basically like a smart feature is one where the difference between the positive and the mean is large, and the difference between the negative features and their mean, and the global mean is large. So it's slightly fancier. It's not terribly clear why that's better than this, but again, it's one that's been used in the micro Okay, let's do something even fancier. Now imagine here we're doing ridge regression from our inputs to our labels, and we're going to do kernel ridge regression. So we're basically predicting the mean of our y's, which are our labels, from nonlinear functions of our x's. Okay. So if we do, this is our ridge regression objective. We want to minimize the squared error in predicting y from V, which contains our feature maps of our inputs. Okay. And we've got the smoothness constraint on our function w, which is nothing from our inputs to our outputs. Okay. The solution. Oops, what's that all about? Anyway. Okay, so here is the solution. So if I solve this ridge regression problem and I plug that back into my objective, this is what I get out, okay? I get something that basically doesn't care about the relation between my inputs and outputs, which is this label matrix transpose trans label, so I ignore that. And then I got y transpose k plus lambda I inverse ky. Okay? So at first sight, like what has this got to do with HSig? Like it doesn't look like it has anything to do with HSig, right? So now let's modify it. So let's assume that we're using as our y's something which has mean 0. Okay? So for instance, the example that we used on our previous slide, this will have mean 0. Okay? So what I've got is the following. So I've got y transpose, and then I've got k plus lambda I inverse k y, right? Now this is a scalar, okay? So I can take the trace of a scalar, and it's still a scalar, okay? Now when I take the trace of something, I can commute the ordering. So I can take this y transpose and put it here. Okay, so let's do that. Take the y transpose, put it at this end. Okay? So now this looks like an L matrix, right? This matrix looks like the dot product between the features of y and the features of y. But is this thing here, is this a valid K matrix? Okay? So the way to see that this is a valid positive definite kernel between features of x is the following. I do an SVD of my K. So K is equal to U, S, U transpose. I know I get the same matrix here and here because K is symmetric. Okay? So when I do this K plus lambda I inverse times K, what this looks like in SVD land, plus lambda I inverse times K, right? When I add lambda I inverse, lambda I inverse, okay? So then I get this is equal to U, and then I've inverted this matrix, so I've got this S plus lambda I inverse U transpose U S U transpose. These are orthogonal, so they cancel. And so then what I've got is U, and then a diagonal matrix, U transpose. What does this diagonal matrix have? DII is equal to the ith entry of S, Si divided by Si plus lambda. Okay? So these diagonal entries are non-negative. So this matrix here is positive definite, so it's a kernel. Okay, so this is just a fancy kernel between the inputs. But what I've done is I've sort of modified the kernel by doing this sort of shrinkage operation on its singular values. Okay? So what I've shown is that if you do ridge regression with a linear y, it amounts to doing HSig. Okay? So this is again just an instance of HSig. Okay, so now a question might be, well, here I've used a nonlinear kernel, although I'm only allowed to, I've used a linear kernel on my y, so I hope you remember the warning I gave at the end of the last lecture about where that can go wrong, which is basically if the mean of the y doesn't vary with the x, but if some higher order statistic of the y varies with the x, this isn't going to find it. So there's your warning again. Okay? So the depressing thing we found when we were doing this sort of article, we were reviewing all of these measures of feature relevance, and we were seeing, when we were looking at microarray data, whether, well, first of all, how well they work, but second, whether it was ever any use to use a nonlinear kernel when you're using HSync. And the sad thing is that the answer was most of the time no. So this very simple idea of just looking at the features with the largest difference in means for microarray data, that works pretty well, pretty much all of the time. And that's because, a lot of the time our classes just have this kind of difference where if this is one dimension and this is the second one, you've got this very simple, linear relation between the feature means and the labels. So basically, feature mean is low, label is -1, feature mean is high, label is +1. And so there is no point in using a nonlinear kernel to find a linear relation. So where might it matter to use a nonlinear kernel? Okay, there are two cases where we found that it matters. The first is, in a binary problem, if you have a class with multiple subclasses, then it can be useful. Okay, and I'll show an example of that. The second case is when you have a multi-class problem, right? So rather than just having binary classification, I have n1 samples with one label and 2 samples with the second label and a samples of the nth label. Okay, and in this case, different features might be good at discriminating different, different elements of this multi-class problem, and so there a nonlinear kernel can matter. Okay, so in this case, I've used this as my L matrix for the multi-class case. It's not the only one, but it's a simple one. Okay, so let's look first at this nonlinear dependence between features and labels. So this is what I mean when I say that I've got a binary problem, but one of the classes is broken into multiple subclasses. So see here, if this is the expression level in some entry of my microarray, then the healthy patients might have just 0 expression, but the diseased ones might have either increase or decrease. There's 2 subclasses where things go wrong. Okay? And if I use a linear kernel, but my feature is either positive or negative, when it's in the same class, then this linear kernel isn't going to find this feature. But if I use a nonlinear kernel, it's like using nonlinear HSync, but with a nonlinear feature map. So what I'm effectively doing is that I'm taking my x-axis and I'm distorting it by this red function here. Okay? So the red function says that if I've got points either here or here, I should make them negative. Okay? And that's what I've done. So I put all my red points here. And if I have points in the 0, then I should push them to be positive. Okay? And so now, once I've distorted my points through this nonlinear function, then I do have a linear relation with the y's. So this is an instance where using a nonlinear kernel for feature selection matters. You've got multiple subclasses, some of which have increased expression, some of which have decreased expression. But they have the same label. The label is sick. And then one class with, yeah. So is that clear? Okay. So the next case where it matters to use a nonlinear kernel is in the case where different coordinates might be useful for discriminating different aspects of a multi-class problem. So what do I mean by this? If I use a linear kernel and I'm trying to sort of tell apart blue from green from red, okay? Here I've got some sort of linear correlation between these 2 features and the labels. But it's not terribly good at separating green from red. Okay, it's sort of, yeah, a bit mediocre. But now if I use a nonlinear kernel, I found here a feature which is very good at separating blue from red and green. And then I found another feature which is very good at separating green from blue and red. So this kind of more complicated interaction is something I can get using a nonlinear kernel, but not using a linear kernel. So if you've got this multi-class problem where you've got multiple labels, it turns out to be useful to use a nonlinear kernel. Okay, so these are the 2 cases.
Can you talk about instances where your method might do a lot better than KNN? Like, I guess looking at some of those examples, you would think that you wouldn't need something so sophisticated to get very good performance.
So when you say KNN, so I'm trying to learn like the relevant features. So what is it that you have in mind?
Oh,
so,
just for classification purposes.
So, okay, so what we are doing, we have like 1,000 features and we're trying to find like the relevant ones. So any classification problem will be easier when you've found a small subset of features that are very dependent on the labels, right? So think of this as a pre-processing step where we're throwing away all the irrelevant features. Yeah?
I actually have a similar question. So why can't we, in the case of the linear kernel, why can't we just use like some other filter-based feature selection method, I don't know, based on information gain or whatever correlation?
Yeah, so you can use, like there's numerous methods you can use to find, if you're using a linear kernel, what we've shown is it amounts to doing something which is reasonably classical, like looking for the difference in feature means. So what we were sort of trying to illustrate with this paper is that like there's a lot of like very simple heuristics that you can write in this way, that's fine. But the other point which we were trying to make is like in what cases does it make sense to use something other than a linear kernel? And there like it becomes a little bit more interesting. Yeah. But you know, the linear kernel one was just to show like where that these methods fit in with this kind of framework. But yeah, like to me this kind of situation here is really interesting because like you've got like it tells you something about your data to know that your seek population is into multiple subclasses. Yeah. Okay, there are more questions about this part. Okay, so now this is quite a fun example. I'm going to learn taxonomies on my data using a dependence measure. Okay, so what do I mean when I say a taxonomy? So a taxonomy is basically an unrooted binary tree. So binary tree is one where the internal nodes have 3 edges. Okay, all of the nodes, all of the external nodes of these trees correspond to clusters. So if I had documents, like these might be documents about cars, these might be documents about trucks, then as I move further away, like this might be bicycles and this might be boats, like something much easier than these two. Okay. So I have a large set of objects and I want to cluster them, put them on these leaves in such a way that the distance between these clusters is like reflective of how similar these objects are. Okay? So what is the distance between clusters? What you do is you follow the shortest path on the tree from one edge node to the other. Okay, so A and B, the distance is 2. From A to C, it's like 1 plus 1, which is 2, plus 2 is 4, plus 3 is 7. Okay? So that's the distance between A and C on this tree. Yep. So, you know, what I have is I'm just given a big bag of points. And I need to construct the tree and assign the points to the clusters such that it has this taxonomic structure. And like this is a structure that people who do clustering really like because it's a very sort of natural way to arrange objects. You arrange them in a tree, like it's very interpretable.
What do the weights of the edges signify?
So the numbers on the edges is just how far, like the distance that one travels moving along this edge. So to travel from this cluster to this cluster, you move a distance which is the sum of the numbers on the edges. So that's what these denote. And you know, you can sort of think of this as a meta cluster, which is a distance 1 from each of these 2 clusters. Yeah. But you know, the important point is that you can always find the distance between any edge node and another edge node by following the shortest path and counting the numbers that appear on the edges. And that's a taxonomy. So this is one way of arranging data. But it's, I think, a very natural one, and we'll see examples specifically. Okay, so this is, you know, distance between A and A is 0, A and B is 2, as we've seen, A and C is 7, as we've seen, by counting the distance on the edges. So if I'm given a set of points, how do I cluster them in a taxonomy, and how is a dependence measure, like what does that have to do with this problem? So let's find out. Okay, so imagine that this, I'm doing here like a really simple clustering problem. Okay, I've got 2 dimensions and I've got 3 clusters. Okay, now if I compute using my exponential quadratic kernel, ground matrix, so the kernel matrix between all pairs of these points, this is the structure I see. So this is actually computed on this data. Okay? And what you see here is you've got these blocks which are heavy on the diagonal, which correspond to how similar these points are to themselves. Yeah? Then you've got these off-diagonal blocks which are a bit lighter. These correspond to how similar points are to their neighboring cluster. Then you've got this very light block here, which is how similar blue is to green. Okay? So that, you can see a very clear structure. And you can approximate this structure by the following much lower dimensional triplet of matrices, or double set of matrices. Okay? So this inner matrix, which is a 3 by 3 matrix, is just the average of the entries here. Okay? So this is on average how similar is blue to blue, red to red, green to green. You know how similar is, yeah, red to green, and then red to blue. Red to blue, no. Green to blue. Here. Okay? So this is just a 3 by 3 matrix, and then these matrices either have 1s or 0s. Okay? And basically a 1 in the first column means that I'm assigning to cluster 1. A 1 in the second column means I'm assigning to cluster 2. A 1 in the third means assigning to cluster 3. So basically I take this tiny matrix here, I multiply it by this long thin matrix, I post-multiply it by the same long thin matrix, which assigns, you know, similarities to these individual blocks here, and then I recover approximately that matrix. Okay? So these pi matrices here, these are cluster assignments. It's either a 1, meaning it's in the cluster, or a 0. Okay? And the number of columns is the number of clusters. This is a cluster similarity matrix. This is the average kernel value between points, you know, between, say, cluster 1 and itself, or cluster 1 and 2, and so on. Is that clear? Okay. So, you know, that's great, but what is going to happen is somebody's going to give me this matrix, and I'm going to have to learn these two matrices. And the problem is that, like, the world won't give me nicely sorted data. So it's not going to look as clean as it does here in my document. Okay, so how do I learn these matrices from this? Okay, so one way that I might be able to do it is to maximize the dot product between this matrix and this matrix. Okay, so this is the kernel matrix, my approximate kernel matrix corresponding to the structure that I believe, and this is the true kernel matrix. And I'm also going to center, like I'm going to ensure that I've got like normalized rows for this thing here. If I do that, then this is indeed like the dependence between the M and the cluster label matrix. The label matrix is something a little bit more complicated now. I should say my cluster similarity matrix. So I'm also doing something which I hadn't done before. I could maximize just HSIC, but here I'm maximizing HSIC divided by this norm here. So does anyone want to guess why I have to put this norm in the denominator here if I'm going to maximize this to learn my cluster structure? So I'll give a clue. What happens if I just increase the entries in this matrix without bound? And I don't have this denominator. So I'm increasing these y's. Without this denominator, this can just blow up. So I could make this objective infinitely large just by making these entries bigger. So what I'm doing is I'm dividing by this so that just making the entries bigger won't help because it'll cancel. And so instead I have to actually learn the structure. So this is something we noticed we had to do. Okay? So I've got my matrix M, I've got my cluster structure. This pi matrix is something that assigns points either to one or to another structure. Okay? So, you know, this is a clustering, right? But I'm trying to learn a taxonomy. So I could just solve for this using spectral clustering, but it wouldn't have a taxonomic structure. How do I enforce that it has a taxonomic structure? Okay? So what I'm going to have to do is I'm going to have to change this matrix here to ensure that my clustered points follow a taxonomy. And I'm also, you know, in changing that matrix there, I'm probably going to have to rearrange some of my points and move them to different clusters so that I get a good clustering. Okay, so let's see what rules a matrix of distances needs to satisfy if it's to be a taxonomy. Okay, so first of all, if I've got a kernel, this is how I get a distance between 2 points using the kernel matrix. Okay, so let's remind ourselves why that is. Right? If I want to compute the distance between features of xi and features of xj, say, distance squared, well, this is the dot product of feature xi, feature xj, the xi first, plus dot product of feature xj, feature xj, minus 2 times dot product of feature xi, feature xj, right? That's exactly what I've got here. So kernel between xi and xi, kernel between xj and xj, kernel between xi and xj. Okay? So when I've got my kernel matrix here, this is how I get the distances between the points. Okay? Now, a taxonomy has to satisfy, the leaves of the taxonomy have to satisfy the following 4-point condition, right? Which is a little bit, yeah? Okay. So basically, this seems a little bit obscure. What it's saying that basically the distance between A and B, so let's say, in this taxonomy, so the distance, let's see, DAB, so DAB, which is the distance, this is a very simple taxonomy, it's only got 2 internal nodes. So I'm saying the distance between A and B plus the distance between C and D must be smaller than the larger of these two, the distance between AC and the distance between BD, or the distance between AD and the distance between BC. So you can see that it's true when I do this second one, this green one. Okay, so this does look a little bit obscure, but it turns out all that it is the triangle inequality applied to taxonomies, so applied to like binary trees. So it's a messy looking condition which is just making sure the triangle inequality holds. Okay. So basically, like, if I've computed my kernel between my clusters, I can then find a distance matrix. I find the distance matrix using this. Then I find, like, approximately the closest taxonomy. So it's NP hard to do that exactly, but we can do it approximately. And then, yeah, once we've got our taxonomy, we can construct the tree. We can draw it. Okay? So this is what the algorithm looks like. Okay? So I start with my matrix of kernels between all of the points in my bag that I'm trying to cluster, which is M. And I start with a cluster assignment pi and a similarity measure between my clusters y, which I just get from some unconstrained clustering. For instance, spectral clustering, or I use my favorite clustering method. Okay? So this is a clustering that doesn't satisfy the taxonomy constraints. Okay? So, first of all, okay, so I've initialized my clustering. I've suggested using spectral clustering here, but you can use some other method. Okay? So given that I've assigned my points to clusters, I now compute the kernels between all of these cluster sets. Okay? Which I can get in closed form. And then I can construct my distance on the basis of that inner kernel, the kernel between my clusters. Okay? Then I find the closest taxonomy. Then I need to go from my distances to a kernel matrix again. So this might, again, seem a little bit mysterious. Like if I've got distance matrices, how is it that, entry-wise multiplying these distances and then doing a centering, why is it that this gives me a centered kernel matrix? So that's something I'm going to show you. Okay? But now that I've changed my kernel matrix, then maybe my cluster assignments were not very good. So I'm going to now update my cluster assignments to improve the dependence between my clustering and my original points. Because I've now changed the distances between my clusters, or the similarity measures between my clusters, it may be that now my points are not correctly assigned to their clusters, so I'm going to rearrange them. And then I iterate this until it converges. So apart from this middle step that I didn't explain yet, is that clear to everybody? So I start with the clustering, I find the distances between the clusters, I fit the closest taxonomy, then I go back to my kernel matrix, I rearrange the points so that they are better assigned according to the cluster similarities I found, then I iterate. Okay, so how is it that this takes me from distances to a kernel to do this, I'm going to again use this idea that I put up here, right? The distance between xi and xj, which is the norm of the difference between features of xi and xj, is given by this expression here, right? So I can solve now for this kernel, right? I just rearrange my expressions, and then I get kernel between xi and xj is the kernel between xi and itself plus the kernel of xj and itself minus this squared distance. So now we're seeing where the squared distance comes from. I've got this entrywise product of the distance matrices, so that's here. But I've also got these terms here, which is slightly annoying. Okay? But the point is that I'm going to be centering my kernel. Okay? And when I center my kernel, if I row and column center it, that means that I pre-multiply by this h, which centers the rows, and that basically zeroes out all of these guys here. Because all of the entries in this row are the same. It's always kx1, x1. So if I've got a constant row and I remove its mean, well, then it's 0. And if I center it here, that removes these column means. So basically these terms here are removed by the row and column centering, and all I'm left with is the squared distances. So that's like just explaining that line. Okay, so now an example of a taxonomy. So this is the famous attractive science data set. So what we have, yeah, one of them used to have hair. Anyway, so there are many, many images of attractive scientists making 3 different facial expressions. So on each of the leaves, I'm representing it like an image selected randomly from the set of images on that leaf. And what you can see is that like this does follow a taxonomic structure, because like the individuals are closely spaced on this tree, and then so they're making different expressions. So this guy, like his expression of happiness is quite similar to his expression of no emotion. So like they're very close. And then the different people are much further away. So if I'm going from this face to this face, like the distance I need to go, like the number of edges I need to add together, is quite long. So this is much closer to this on my taxonomy than to this face. So this was fit from images taken from a webcam using the algorithm that I just described. So you might think, well, okay, I can fit a taxonomy, but what if I just did a normal clustering, right? So what I'm showing here is basically like the level of codependence of the clusters and the labels. So in this case, like this, a smaller number means a better fit. Okay. So here is what happens when I just do a spectral clustering with no taxonomic structure imposed. And the level of agreement with the labels that we know are true, because like we've labeled the images ourselves, is much poorer than if I enforce a taxonomic structure. Okay, so basically I know that my sample conforms to a taxonomic structure because I've constructed it to have that property, right? And what you can see here is that like enforcing that structure means that I get a better clustering. I get a clustering whose labels correspond better to the ground truth. Because it's like I'm imposing a prior. I know that my data follows a taxonomy. I impose that as a prior, I get a better clustering. You could also just impose a hierarchy where you don't know the length of these edges, but you just assume them in advance. And that gives a better clustering than a flat clustering, but the taxonomy is much better, again. Yep?
Does this have an application when you don't actually know the labels?
Oh, so here you don't know the labels. This clustering is completely unsupervised, right?
Okay, but you just have.
Yeah, so basically where we know the labels here so that we can validate, like basically so we can prove to ourselves in this example that the taxonomy that we learn does correspond to the structure that we see. So obviously, like if you really have a clustering and you don't know in advance, then you just have to look yourself at each of the clusters and see if that makes sense.
Okay,
Yeah.
so that would be the only way to validate it.
Yeah, no, that absolutely, because it's clustering, like, yeah, if you have labels, you would use them, yeah. So here is some a taxonomy that we learned from the NIPS data set, okay? So this is NIPS papers only up to, I think, like early 2000, so it's not quite the topics that are being done these days. or not entirely. But what you can see is that, like, this taxonomy makes sense. That, Bayesian and discriminated learning are closer to each other than reinforcement learning, which isn't very close to neuroscience. What we've got here is an extra cluster called miscellaneous, which basically means that we probably use more clusters than there are natural clusters in the data, at least the way we're doing it. So how did we get these cluster labels? What we did is we looked at words that occurred in these clusters, with the highest sort of difference in frequency compared with the total set of documents. Okay, so these are words in those clusters that we noticed happen much more often in those clusters than in the rest of the documents. So these are not labels from supervised learning; these are labels from us observing the clusters that we got and seeing which words are most common in those clusters relative to the population. And again, it's making sense. In neuroscience, like the most discriminated words are neurons, cells, model, blah blah.
But why is RL so far from your side?
So RL, at least, I don't think that, if you look at the neuroscience words, you've got, at least at the era when these papers were written, like cell activity, synapse response, firing back, there's a lot of like cell level modeling, like, individual keys fighting neuron. Whereas RL, we've got state, learning, policy, action, reinforcement, optimal control. Like, it's pretty clear, at least from the discriminated words, that these categories are like quite disjoint in this corpus. Yeah. So yeah, so this works pretty well. Okay, so Fernando, what is the schedule?
So
Sorry?
I think we can do the panel now.
Yep. Okay.
So
So
yes.
yep, I will stop there.
Okay.